Announcements on homework 3. I think I made a Piazza post on this. One thing you're going to need to do when you're using Maple to solve this problem is if you don't tell Maple enough information about the, say, constants that are involved, it's going to have a hard time finding the right solution to the differential equations. So if it doesn't know, for example, whether the constant that you're multiplying your temperature term by is positive or negative, it might give you the solution assuming it's a negative. And if you then plug that into ease, it'll complain and say, I'm trying to take the square root of a negative number or something like that. So to fix that problem, you need to use this command called assume. So I've written it kind of small here, but the idea is that in Maple you would say at the beginning of your program, any constants that you want to tell Maple are always positive, you would just say assume parentheses the variable name or the parameter name. So if, let's say you called that parameter A, and then it's followed by 2 colons, and then the quality, so positive. If you have multiple of those, then you say comma, B, positive, and so on. And that's going to force Maple to assume that those constants are what you want them to be. So that might be something like, conductivity is always positive, resistance is always positive. Those things that end up multiplying your temperature terms, you want those to be positive. So hopefully that makes sense. Second thing is, I guess I didn't state it in the problem, but just assume that the heat exchanger is long enough in the direction of the page that you can neglect heat transfer. So you're not trying to do an ODE that's solving for a coupled temperature while also losing heat from the top and bottom, right? So just kind of treat it like it's a 2D problem. Okay? Any questions on that stuff? All good. All right. Let's briefly recap what we were doing last time with this mess of a page. So remember what we're trying to do for 2D problems now. We're going to use this separation of variables technique. Separation of variables, we go through the process of writing our differential control volume. It's differential in both x and y. And we're keeping track of the heat flows both in x and y. And we end up with Laplace's equation, which is the second derivative of temperature, equals 0. And then we had these 4 boundary conditions. We have temperature at x equals 0, heat flux at x equals w, and a similar kind of setup for y. So let me just, so we have this information. Now our job is to figure out how to solve this problem. OK, so going to this page, let me just clear this stuff off. So let's go through this process. Like I said, there's maybe 6 or 7 steps that we have to go through. And we'll just walk through all of them, and we'll talk through it using this example. OK, so step 1 in using separation of variables is, step 1. We're going to check that your problem meets the requirements for separation of variables. So check requirements for separation of variables. And if it doesn't meet the requirements for separation of variables, you can't use separation of variables. It's that simple. So what are the requirements? Well, there's 4 main requirements. So requirement 1 is going to be that the PDE and the boundary conditions must be linear. Right, linear. So that means all that stuff that we see up there, none of that involves temperature to a power. None of it involves any kind of function that makes temperature nonlinear, right? So this set of equations does satisfy the linear requirement. Again, remember, we're taking the second derivative. That doesn't make it nonlinear. It's just taking the derivative of a linear function. It's still linear. So in this example, our PDEs and our boundary conditions are linear. So we can proceed with that part of it. The second thing is the computational domain must be simple. must be simple. All right, what does that mean to have a simple domain? Well, let's actually look back at the previous slide here for a second. If I have a domain in which the boundaries of the domain fall on a constant value of the coordinate, that's simple. So here we have our rectangular surface or rectangular geometry in X. The boundary falls on a constant value of Y, right? For both Y equals 0 and Y equals H. And the same thing is true for X. So this Cartesian coordinate system is a simple setup. If we had maybe cylindrical coordinates, that just means you're taking a slice where it's constant values of r and theta. Or spherical, it's going to be phi and theta. Right? So as long as you have constant values along the, or constant boundaries along the domain coordinates, it's simple. Again, for this problem, that checks out, so we can proceed. Criteria 3 is the PDE must be homogeneous. All right, looking at our PDE, so we see the partial with respect to temperature in both x and y is equal to 0. So check, right? That is satisfied. What it would look like if it wasn't homogeneous is that there would be some constant term or some function of the independent variables on the right-hand side of that PDE. So again, that's satisfied. Then the fourth criteria is both of the boundary conditions in one direction must be homogeneous. This one is really important, right? This is what gives us the ability to use separation of variables, is that we can take the problem, solve it for both the x variable and solve it for the y variable, and then bring it back together. And that only works if, in at least one direction, both of the boundary conditions are homogeneous. So let's look at our boundary conditions up in the right hand. Looking at those boundary conditions, which direction, x or y, is going to be our homogeneous direction? It's a little hard to see. Correct, right? We have x equal, t at x equals 0 is 0, and the differential dt dx at x equals w is 0. So our x direction is homogeneous. Y is not homogeneous because th is not 0, right? Now, if we had a problem where both directions were homogeneous, what is the solution to that problem? Right? Temperature everywhere in a problem where both directions of the boundary conditions are homogeneous is 0. It's not an interesting problem. Right? It's a trivial solution. So in any interesting problem, you're always going to have at least one direction that has a non-homogeneous boundary condition. In this case, we have 3 of the 4 boundary conditions are homogeneous, but the 4th one is what makes anything happen in this problem, that t at y equals h equals th. So, okay, we can move forward. We know that we've satisfied all the 4 criteria. You're going to have to do this every time you do a separation of variables problem.